All right, so today, as promised, we will be able to compute some very explicit examples. So to say, collect some fruit of our labor. Here is some fruit from my backyard and front yard. Well, this time of the year, I have many, many roses and peppermint. So feel free to take as many as you need, virtually, of course. But you're welcome to stop by physically if you can. So let's recall what we did last time. We defined the simplicial set of functorial field series of dimension D with geometric structure S and the category of values capital V. So this was defined as a derived mapping simplicial set from the smooth symmetric monoidal infinity D category of D-dimensional Bordisms with geometric structure S to V. And last time we've stated the geometric Bordism hypothesis, more precisely its locality part, which tells you that the functor that sends S to board ds is a left adjoint functor. It has a right adjoint, which is what we denoted by V cross D, a notation which is motivated by the second part of the GCH, which tells you how to compute V cross D. So here you now have on this side you have a derived mapping simplicial set of sheaves on the side FMD. So here so this is difficult on this side. This is difficult to compute. This side is much easier to compute because it's just sheaves on FMD. And we also discussed how we have a recipe to compute V cross D. V cross D, if you recall, being a right adjoint, we discussed how V cross D has a very simple definition. It's just literally, quite literally, the simplicial set. So its value at some, say, object in the site. And here I'm only dealing with, well, I guess I can still indicate an arbitrary object, that's fine. This is quite literally thanks to the fundamental property of adjoint functors. This can be defined quite literally as f of t, d, and the geometric structure will be precisely the representable geometric structure. Omega of t over u. And of course, this immediately raises questions: how do we compute such a thing? This is where the second part of GCH comes to the rescue.
Dmitri, quick question.
Yeah.
The unit embedding. So the unit embedding, are you taking the enriched version or the non-enriched one?
Yeah. So here, I guess I'm talking about the enriched version. But in principle, if you prefer, it is also certainly possible to. I mean, there is an adjunction. Maybe I should have. I think I mentioned it before, but let me just quickly mention that there is an adjunction between unenriched sheaves and enriched sheaves, where the right adjoint simply restricts restriction functor. I guess we can indicate this as a iota upper star, where iota is the inclusion of the unenriched side into the enriched side. And it has a left adjoint, I guess, which we can call, okay, you guys screw up. No, that's fine. The restriction functor this is iota shriek, and iota shriek is a continuous functor that sends a representable presheaf on the unenriched side to the corresponding representable presheaf on the enriched side. And therefore, thanks to this junction, in the case when your geometric structure S, if S has the form iota shriek of some unenriched geometric structure, let's call it, I don't know, S prime, then of course you can see how this junction allows you to compute this home on the right side. So a scar can be computed as derived mapping space. Mapping simply shows set from S is iota shriek S prime, so you can put S prime here and move it to the right side, iota upper scar of V cross D. And iota upper scar of V cross D is just the usual, it's basically the same V cross D, but now as an unenriched presheaf. So in principle, you have a version for both enriched case and the unenriched case. And maybe in practice, most of the geometric structures actually arise in this fashion. So in principle, this is a very practical observation and a very practical recipe.
So I assume that it doesn't matter whether we take the enriched unit dilemma or the non-enriched one. We will get the same result for the Bordism category, or is that not true?
That's right. So if you want, you can construct this presheaf directly. This whole expression, you can construct it directly by basically taking the let's see. Let me see if I can. By only looking at morphisms of representables in the ordinary sense, right? Because the difference between enriched and unenriched is that in the enriched case, you also allow smooth families of morphisms, whereas in the unenriched case, you only have a discrete set of morphisms between representables. And this expression here, you can clearly translate both an unenriched presheaf and enriched presheaf, depending on your preference. So, but I guess, yeah, so in principle, it's fine to assume the unenriched Yoneda here.
So iota shriek of unenriched unita is enriched unita?
Oh, yes, of course. Yeah, I should have mentioned this.
Okay.
Let me just. I guess I'm not really sure how to even write this. But this one is unenriched and this is enriched. I guess I used to put E and R as a subscript, so we can do this again. Yeah. So iota shriek by definition is defined through this expression, which then uniquely determines the whole functor, because left adjoint functors out of sheaves have a universal property. They are precisely functors out of the underlying psych that send check nerves to equivalences. The check nerve diagram is sent to a homotopy colimit diagram. All right, so in principle, you have recipes to compute both in the case of enriched structures and unenriched structures. And GCH part 2 tells us how to compute this V cross D in much, much simpler terms. And what you do is you guess some map from W to V cross D, which you expect to be a weak equivalence, but you don't have to show it's a weak equivalence yet. So instead, you only have to write down some map. And this is much easier than you, well, let me put it this way, it's maybe, there's some degree of effort you have to put in here, but this effort is a reasonably straightforward effort. It's a bureaucratic effort. It's not creative effort. So you have to deal with some bureaucracy of writing down a morphism of smooth, symmetric, monoidal, infinity D categories. But it's not like something you have to think hard about. And once you wrote down such a candidate map, to show it's a weak equivalence, you can use a trick. And the trick amounts to the following. To show it's a weak equivalence, let's evaluate on some object on FemD. And here I implicitly restricted to objects that are projection maps for a product of U and RD. Because this allows for a simpler formulation, and in any case, this is sufficient to check you have a weak equivalence in the Czech model structure. So you take this map, you evaluate it, and then you have the evaluation map for the geometric cobordism hypothesis, which takes a functorial field theory with a representable geometric structure given by this map, and evaluates this functorial field theory on zero bordisms that are connected. Connected zero bordisms are just points with a germ of a geometric structure. So this is evaluation map on connected zero bordisms. In other words, points with a d-dimensional germ of a geometric structure, and of course cuts. So a typical, just to quickly remind you, a typical, for example, in dimension 2, a typical picture would look like this. And you also have a preferred side on the horizontal and vertical direction. And you have a germ, so a little ball where the geometric structure lives. In the case of a representable geometric structure like here, the geometric structure is simply embedding into RD. So this little ball is embedded into RD. And you can literally imagine your, so let me just say this is embedded into RD. So you can literally imagine your ball sitting inside RD. You can identify a bordism with its image in RD. So it's literally such a picture inside RD. And you evaluate your functorial field theory on such pictures. And GCH part 2 tells you that this map is a weak equivalence. And therefore, to show that this map here is a weak equivalence by the 2 out of 3 property of weak equivalences, you might as well show that the top map in reg is a weak equivalence. And what's the advantage of looking at the top map? Well, this composition, this whole composition is much simpler to work with because this is just a, yeah, I should have mentioned to you, of course, that V cross means discard non-invertible morphisms from V, and take is fully dualizable objects. I should have mentioned this too. Take fully dualizable objects and take invertible maps between them. So this is just a this is no longer an infinity D category because I threw away all non-reversible morphisms. So this is a symmetric monoidal, smooth symmetric monoidal infinity groupoid. And if we evaluate it at U, this is just a symmetric monoidal infinity groupoid. In fact, we don't really care about the symmetric monoidal structure here at the moment. So this is just a simplicial set. Just like here on the left side. So you also have to check a weak equivalence of simplicial sets. Weak equivalence of simplicial sets. And that's why it's much easier to do this than to check that something like here is weak equivalence, because this map only talks about the geometric structure, or more precisely, your candidate answer W, and the invertible part of the target. Notice it does not talk about anymore about any functorial field series. So everything is concerning functorial field series happens really fast. You write down a map, you compose it with the evaluation map on connected zero bordisms, and the whole composition no longer involves any field series. And so this map you have to show is a weak equivalence. So this takes care about the first ingredient in the right side, how to compute this object. And so this reduces the whole problem to computing the derived map in simplicial set from S to W. And here is a recipe how you can do that. The recipe tells you to, well, it's a recipe to do both. You can either elect to compute, you can elect to construct individual points in this mapping space, which correspond to functorial field series, or you can elect to construct, compute the whole space, which will compute the whole space of functorial field series, which is important for stuff like the Stolz-Geithner program and many other applications. And we already reduced the problem to computing derived map in simplicial set from S to W. So now the next step will be to construct, to compute this derived map in simplicial set. Notice being derived means in principle you may have to choose resolutions. And here I did mention this explicitly. You can pick a resolution from W to W prime, replace W by W prime, and compute derived maps to W prime instead. This step may be optional in a sense that if it is your goal to construct only some points, some examples of functorial field series, then it may be unnecessary to choose a resolution, because perhaps this choice already works fine. You can construct a map from S to W, which will automatically give you a map in the derived mapping space, because the ordinary mapping space maps into the derived mapping space. And the point of choosing a resolution that mostly applies to the first part. If you want to compute the whole mapping space, then you would have to guarantee that this map is a weak equivalence. This map is a weak equivalence if, say, S is cofibrant and W is fibrant. So some replacements may be necessary. In the injective model structure, every S will be cofibrant, so only a fibrant replacement may be necessary. And we'll see it's in principle easy to construct injectively fibrant replacements, at least in some situations, because, for example, the Gram complex is an injective resolution. And finally, after we are done with all this, we want to compute the ordinary either ordinary mapping simplicial set or using natural operations, or we can apply the equivalence to from sheaves on the enriched site where both S and W currently live. There's equivalence to sheaves on Cartesian site with values in simplicial set equipped with an action of OD. And OD here is understood as a topological group or infinity group. So that's equivalent to GOD, which in its turn is also equivalent to the monoid of embeddings of RD into itself. Enriched monoid, so also considered with this topology. So these are all equivalent in this setting. And then we can compute maps of stacks over Cartesian spaces, which in practice may be even easier than maps here, but we also have to remember they must be OD equivariant. So today I will do some explicit examples, so all those recipes will be applied to compute maybe some functorial field theories. Okay, any questions so far before we move on to examples? All right, maybe it's time to split, I don't know. All right. I realized maybe I picked an example that is a bit too difficult, but nevertheless, it will illustrate some of the main points. The category V, so, okay, we'll first do the first part of the recipe, which is compute V cross D. And then we'll do the second part of the recipe, which is to compute the derived mapping simplicial set. So here's maybe some example for non-trivial example for the target category V being the default delooping of U1, complex numbers with absolute value 1. This is, of course, precisely the target for pre-quantum field series, because the action functional, you remember in quantum field theory, you always see expressions like exponent I over h bar s of some fields, let's say phi. This is an element of U1. And so it's the same U1 as you have here. And maybe one point to make here is that this expression is sometimes a bit of a lie because it doesn't really correctly explain the topological receptor. And from our point of view, what the explanation is, it's the maps here, they compute differential cohomology, and differential cohomology requires also some topological information, some integral characteristic classes. Let me also very briefly remind you what this d-looping is. The idea is very simple. You have a single k-morphism for if k is between 0 and less than d. And then d-morphisms are precisely U1. So for instance, if d equals 1, you see a groupoid with a single object, and automorphisms of this object are U1. That's precisely the d-looping of U1. And in the language of single objects like viscosity, let me just very briefly remind you, there is a forgetful functor from delta to gamma that sends an n-simplex n, which you think of as a chain of n-composable arrows and here, I guess ultimately I realized that the model with finite sets and partially defined maps for gamma is much better than pointed sets. So let me use just finite sets and partially defined maps as my model. Then you assign it to a finite set, which is just a set of arrows, n arrows in this chain. And then to define the d-looping as a functor from gamma times delta d to simplicial sets, let's take our original gamma space z. In our case, this will be U1. And let's compose it with this functor from gamma times delta d. You first apply the forgetful functors that linear to gamma times gamma d, or in other words, gamma d plus 1. And then there's a monoidal structure on gamma, which is given by the product of sets. This monoidal structure, let me emphasize, it's not Cartesian, because the product of sets is not the categorical product of in this category. The categorical product in this category will be different. And this construction, being basically a left-adjoint functor, it doesn't produce a vibrant or local object, so you would have to manually enforce globularity and completeness. And so what you get after all those steps will be that an object in gamma will be a bunch of simplices will be sent through, and what we have here is L copies. So this takes care of the L part. And then for each of the L elements, you have a copy of, and here I have, this may come out of the blue maybe a little bit, but what you see here are cubical cochains on the product of these simplices, which you interpret as cubical sets. And in case you're wondering where all of this is coming from, it's basically implements the following very simple idea. So for d equals 1, for example, you would see for d equals 1, you would have a single, this should terminate in d, I guess. A single simplex M1 will be mapped to the nerve of a category whose objects are chains of arrows of length M1, and each arrow is equipped with an element of copy of U1. So let me call it A1, A2, A3, A4. And this is not just a set, it's also a groupoid. We do want completeness. And the way we see the groupoid structure will be the 0 cochains here, which will look like, let me just put another object here. And you have vertical arrows, and each vertical arrow will be equipped with an element of your groupoid. F1, F2. Sorry, I should have started with 0. Which is, of course, precisely the RESC nerve, of the category of given by the ordinary de-looping of U1. If you recall, we drew such pictures precisely for the RESC nerve.
Sorry, Dmitri, what is C infinity UA?
C infinity.
What is U and A in the definition on the right?
Oh, yes. Oh, yes. Sorry. Of course, A is just U1. This construction works equally well for an arbitrary abelian Lie group A.
And I guess the U is then just like the Cartesian space we have as an input, right?
Yes, that's exactly right. So, in fact, I should have mentioned this. Yeah, it appears, of course, as a first argument, the Cartesian space. Yeah. Sorry about that. Yeah, I think this should result.
So one more question. So the idea is really you have this default delooping, but at first you really only have it as a sort of just as a pre-sheaf on gamma times delta to the d power. So then you have to make it fibrant so as to be an infinity category in the proper sense. And the fibrancy construction is what you just did.
Yes, precisely. So that's what I mean by enforce, because what you get from this naive composition, it will not be complete. For example, why is it not complete? Well, imagine you are looking at the object, for example, 1 in gamma, and then a bunch of zeros. In a complete Siegel space, n-fold Siegel space, the value here should encode the infinity groupoid of objects and invertible morphisms. But let's see where this functor maps this kind of data. Well, 0 gets mapped to the empty set. So you are going to map everything to the object. Yeah, you are going to map everything to the object 0 to the of gamma. So this will map to 0 in gamma, and the value on 0 is contractible, which I mean is perfectly fine from the viewpoint of model categories, because you are allowed then to take a Feynman replacement, and the Feynman replacement will find all invertible morphisms in higher simplicial degrees, and it will place them into this position. But that's a non-trivial process. Oh, and the other thing, of course, is that globularity also must be enforced separately. Yeah. Yeah, so strictly speaking, I guess I should have, in one of the previous lectures, I should have maybe described this construction in more detail. It clearly deserves to be described in more detail, but sorry about that. Yeah, so this is what you get after completion. Yeah, and notice globularity means, well, I guess it doesn't mean anything yet because I need to draw a picture for d equals true. I mean, for d equals true, you will see maybe a similar picture. Now, an object in this groupoid will be a two-dimensional grid. For example, this one. Too many arrows. Well, you can imagine. And now in each two-dimensional cell, you will see an element of A. Yeah, let me call it A11, A12, A13, A21, A22, and so on. And then this data is organized into a groupoid. I mean, I guess this is a big, to call this cubical cochains is a bit too fancy at this moment, because of course the only non-zero group will be the grouping dimension D. So really I should have just said take D cells here and map them to this set here. Yeah. And then such grids have isomorphisms between them, and yeah. Okay, so now I have to guess what W should be, and I have to guess a map from W to this V cross D construction. And there are many obvious guesses for what W should be. So let's recall what we already know about W is that W should be a pre-sheaf on the side FMD, whose value at some object should be weakly equivalent to V cross evaluated at U, which in our case can be simply computed as a default delooping of smooth functions on U valued in U1. Well, here is one candidate. I mean, there are many candidates. In fact, next page has another candidate. But let me just describe very stupid and primitive candidate, which is take T over U. And map it to the simplicial set given by the default delooping of smooth functions from T to U1 that are constant on each fiber. So fiber-wise constant. What does it mean to have a function on Rd times U that is constant on each fiber of this projection map? Well, that means precisely the whole fiber gets mapped to an element of U1. So for every point in U, you have an element in U1. This element depends smoothly on U. But of course, that's just the same data as a smooth map from U to U1. U may not be such a good letter, it conflicts with U1, I guess. So you can see how, I mean, this is extremely primitive example, but it does show you that how easily a pre-sheaf can be promoted to a pre-sheaf on cart, like U1, can be promoted to a pre-sheaf on FemD, like this one. So that's the promotion. And let me give you also one more example, which really tells you like other options, how to choose W. And the other example would be, let me keep this one on this page. The other example is, of course, take T over U. And we are going to send it to the chain complex, or more precisely, since we need a simplicial set, I really should say here, not a chain complex, but take a chain complex and then apply the gold con functor gamma that converts it to a simplicial abelian group, and then forget the abelian group structure using the forgetful functor. And here I have another conflicting use of U. Sorry. So I guess I should maybe use a curly U to just. So this is just a forgetful functor from simplicial abelian groups to simplicial sets. What is a chain complex? It's a fiber-wise gram complex mostly. So you have in degree, let me mark degrees here, in degree 0, 1, and up to degree d minus 1, you have, yeah.
would you not like to take the nerve of the abelian groups? Is it really the forgetful functor?
Well, yeah. Here we just need a simplicial set, right? So the point is, I wrote down a non-negatively graded chain complex. I converted the simplicial abelian group using gap, and I forget the abelian group structure to get a simplicial set, and that's what I need to get this functor, right?
Yes, thank you.
Yeah. So it will be this chain complex. So in the corresponding degree, I have differential forms, more precisely fiber-wise differential forms. So the subscript U reminds you of the fact that it's a fiber-wise differential forms over this object. So in more primitive terms, the only vectors you are allowed to substitute in such differential forms will be vertical tangent vectors. The tangent vectors to capital T that the projection map to U sends to 0. And for every such a set of vectors, I have so little a, by the way, is a Lie algebra. Lie algebra of the abelian Lie group capital A. So for the case of U1, the fracture A is going to be just the Lie algebra of U1, which is just the imaginary numbers. Well, some people omit I and prefer to carry it around. I find this very annoying. So you have such differential forms while it is a Lie algebra. And in degree D, instead of putting 0 forms, here I will put smooth functions from capital T to the Lie group capital A, or in our case, it will be U1. Notice there is no difference between fiber-wise, smooth functions, and just smooth functions on the trackable space. Every such function is a fiber-wise smooth function by definition. And you have the usual differentials, the Gram differentials in all degrees except for the very last degree. And here the differential is literally the differential from differential geometry. If you have a smooth map from T to A, it induces a map of tangent bundles from the tangent bundle of T to the tangent bundle of capital A, and the tangent bundle of a Lie group is a trivial bundle. It's a trivial bundle whose fiber is a Lie algebra. This gives you precisely a differential one form here. So this differential is just a tangent map, basically, in disguise. So that's the other resolution W. And it may look quite different from what we wrote down previously here, but do notice it is in fact exactly the same. So maybe I should write it in more detail. The inclusion map from fiber-wise constant functions and I guess here I'm switching to U1. Let me put in general capital A, which is in our case U1. And remember, default delooping in chain complexes is just a shift in degree, in chain degree by D. You can include this into this truncated well, it's called Gallien complex. Without this term, it would be the Gram complex if you put zero forms here, but with this adjustment, it's called the Gallien complex. So let me briefly denote this by omega at most. The U is slightly imprecise, but you can understand what's going on. And let me put capital A just to remind you that in the last term you do have capital A. And so I claim this inclusion is just a quasi-isomorphism. And this is just the Gram lemma in disguise. So why is that? Well, the traditional Gram lemma would tell you that this chain complex is exact in almost every term, except possibly for the last two. And it's also exact in the zeroth term, which may not be entirely obvious, but let's make an observation that a fiber-wise differential D form on a submersion of relative dimension D has as its Gram differential a D plus 1 form, which vanishes because on a D-dimensional manifold, every D plus 1 form will be 0. So such a D form is always closed. And for that reason, you also have exactness in this term. This map is surjective onto closed forms. When I say surjective, I mean in the sense of sheaves. So you have an epimorphism of sheaves. Of course, it need not be surjective if T is something else than RD times U. But if T is RD times U, then it will be surjective. This is just Gram lemma in families. Yeah, so in this term, you have exactness because of the dimensional restriction. And finally, we have to analyze what happens in this term. The homology in degree D will be the kernel of this map. And this map, if you may recall, is precisely the tangent map or the differential. So the kernel consists of functions with a vanishing fiber-wise differential. Vanishing fiber-wise differential means your smooth function is fiber-wise constant. A function with a vanishing fiber-wise differential is a precisely fiber-wise constant function. So in this degree, the cycles in degree D will be precisely fiber-wise constant functions. In all other degrees, you have a vanishing homology. So altogether, you see you have a quasi-isomorphism.
So
So you have, yeah.
By the Ram lemma, you mean the Functorial lemma? Yes.
Oh yeah, sorry. I guess I should. Yeah, probably you're right. Yeah, Functorial lemma. Yes, definitely. I guess I meant the Gram theorem, but that's more general than what we need here. Yeah. Okay, so you have two very different looking but weakly equivalent W's, and in principle, we can write down this map for both of them. It will be more transparent, perhaps, to write it down for this resolution because it will be immediately clear what's going on. I mean, this is not to say it's impossible to do it for the other resolution, but it will be maybe less transparent. So let me just fix our attention on this choice here. And I want to write down a morphism from, let me put it on the left side. Let's see, which is better. Yeah. Okay. So I want to write down a morphism, the green morphism here. So what I do is I recall that V cross D by definition is the derived mapping simplicial set from the board D with a corresponding geometric structure through V. So by adjunction, I have to write down a morphism I guess I skipped too many steps here. So let me actually write it down properly here. So we want to write down a map from W to V cross D, which by definition is derived mapping simplicial set from board D blank to V. And so by adjunction, so to write down this map, we write it down for we fix some object in our RD times U over U. So what we need is to write down a morphism from W evaluated at RD times U over U to R map board D RD times U over U. Now I can use the properties of derived map in space to move this thing to the left. So I have a morphism. Equivalently, I need to write down a morphism of this form. Where here, notice this is just a simplicial set. And it's where this gadget is complicated, it's a smooth symmetric monoid going into D category, but it is in particular a simplicial presheaf. And so every value of the simplicial presheaf can be multiplied by this value here using the usual Cartesian product of simplicial sets. Okay, now let me maybe illustrate something non-trivial about this. Let me perhaps explain what happens on D bordisms. So let's evaluate on let's evaluate on some object, like a Cartesian space, capital V, an object of gamma, which is 1, and maybe a bunch of 1 simplices. Which is how you encode dimorphisms in a complete and full default single space. And we have to land in V, this is a curly V, evaluated on the ordinary, ordinary V was not a good letter, but then the same objects, and a bunch of ones, D of them precisely. Okay, now let's unfold all these constructions. So W evaluated on this object will be a U gamma of a truncated Gaussian complex. And there are all those other terms here. This evaluation here will be V-indexed smooth families of D-dimensional Bordisms. So basically a picture looks like this. Let me draw a picture for dimension 2. These Bordisms are equipped with an embedding into RD. And also, of course, capital V maps to U. So we have a map from V to U, and the Bordism is equipped with an embedding into RD, or more precisely, a smooth family of such embeddings, one embedding for every point of capital V. As usual, I can identify a Bordism with this image under this embedding. So I literally think of this picture as a subsets of RD. And from this data, I have to produce for you something on the right side. Here. And what is the right side? Well, the right side is a groupoid. What are its objects and morphisms? Well, let me say what the objects are. Objects will be just smooth functions from V to U1. And the interpretation here is quite literal, that here we evaluated on these guys that extracts dimorphisms, or more precisely is V-indexed families of dimorphisms in, well, what in our case is D-fold D-looping of U1. And a dimorphism in such a D-looping is just an element of U1. So a V-index family will be a smooth map from V to U1. And let's not forget, we also have some isomorphisms in this groupoid, which I'm not going to talk about right now, but it will be basically some elements of the same type placed on a cube of dimension D. So, but we already have everything we need to see such a functorial field theory intuitively. Let me explain what happens on objects. Objects in this simplicial set will be its vertices, and vertices will be just elements in chain degree 0. which is precisely fiber-wise D forms. So on objects, I take a fiber-wise D form omega, and here I take an object here, which is, well, basically the same picture. It's a smooth map from V to U, together with a V-indexed family of embedded Bordisms into RD. And I have to produce for you an object here, which is a smooth map from V to U1. So let me denote the differential form by omega. Let me call this map F, this Bordism B. So given the data of omega, F, and B, I have to produce for you a smooth map from V to U1. Well, that's very easy. First, let's take omega and pull it back along F. And when I say pull back along F, I mean F as a map of base spaces. So the pulled back form will be a fiber-wise differential D form over V. And here RD times V projects onto V now. Now, once I pull back and I have this fiber-wise form on in V families on RD, let me recall that B is a V-indexed family of Bordisms embedded into RD. So what I can do is I can take this form and I can integrate this over B. And the result will be, if you integrate a D form over a D manifold, you get a fiber-wise zero form. So maybe I shouldn't say fiber-wise anymore. So I integrate, I get a number. I get a number for every point in V. So let me say this is a smooth function from V to what exactly? Well, let's not forget this was formally speaking a form valued in the Lie algebra, and the Lie algebra of U1 is imaginary numbers. So let me retain this detail here. Strictly speaking, the Lie algebra of U1. And guess what? Now I can change the exponent. Now we are valued in U1. And that's what you want. And notice, this is very much, of course, in the spirit of what you do in physics. Because in physics, you would have expressions like exponent of I over H bar S of some field. But what is S? Typically S, the action functional, will be the integral over your space-time or world volume, which is a Bordism, B. And here you will integrate some Lagrangian density L, which is a differential form of the top degree, like omega. So basically, you see now exactly the same expression as in physics. The only maybe trivial difference is that in physics, there is a preference for Lagrangian to be real valued, so I, the imaginary unit, will have to be moved out, but that's a complete tautology. I mean, it's not really relevant. And the other aspect of physics is that the units of Lagrangian can be non-trivial, like the Lagrangian is not a dimensionless quantity. It has units, the same units as the Planck constant, the action. Action has non-trivial units. Action is basically energy times time, I guess. And so to convert back to a dimensionless quantity that you can take the exponent, well, you have to divide by the unit of action. This is the unit of action. The elementary action, if you want, yeah. H bar, the reduced Planck constant. So that's, I mean, so this factor is just motivated by the choice of units for Lagrangian. We want it to be real valued and take the units of action. So what this factor does, it converts it to the appropriate dimensionless quantities. So basically, what we call omega is just I over h bar L. Okay, any questions so far? Okay, so as you have seen, it's I mean, of course, I omitted some details, but the essence of the argument is already present in this formula. And let me assure you, the remainder of the construction is basically not much different from this formula. So there is no non-trivial topology, for example, in the game here. It's all integration of differential forms. The takeaway from here is that it's easy to write down such a functor or such a map. This is just some integration of differential forms. In particular, it's kind of like you should not be thinking here about the traditional difficulties with constructing TQFTs, for example, because this is an entirely different setting, and the difficulties you encounter for TQFTs are completely gone here because there is no non-trivial topology in the game. All topological entities you see here are trivial entities.
Sorry. What is the mechanism of appearance of the exponent function and the integration from
It's our choice.
Formally?
There's no mechanism, it's just the way we choose to do things, because that's a natural way to write down to produce, like the question is, what kind of natural construction do we have that takes as an input differential D form, fiberwise differential D form omega, and a map F and such a V-indexed family of Bordisms B, and produces from this Giga the smooth map from V to U1. Well, pretty much turns out the only thing you can write down will be this exponent. Probably you can even prove maybe a result like this, that you can actually that's the only thing you can write down, maybe up to some multiplicative constant here, but it's really the only thing you can write down, yeah. But ultimately, it's our choice what to write down here, and we just choose to write down this expression here. The exponent, by the way, is I mean, maybe I should mention perhaps one thing at least, that when you want to rank inside a Lie group, of course, you have forms while in the Lie algebra. How do you get from a Lie algebra to the Lie group? Well, you have the exponent map from the Lie algebra to the Lie group. So that's, by the way, this map here is called D-log sometimes. You can see why, because if you have a smooth function while in the Lie group, what you can do is, at least locally on T, you can apply the inverse of this map, and then you can take the usual gram differential of a zero form value in the Lie algebra. So that's so roughly speaking, the reason you see the exponent is because this differential involves basically the differential of the logarithm. That's one explanation for the appearance of the exponent.
Okay, and what about the integration?
Well, again, like it's basically the only thing you can write down here, because you have a differential D form on RD, and you have a Bordism B also on inside RD, and somehow you have to produce from this an element of U1, and moreover, and this is maybe something I didn't mention here, is when you glue Bordisms together, of course, if you glue two Bordisms together, say this Bordism, you integrate a form over this part, B1, you integrate the form over this part, B2. Of course, you want the composition is preserved. So the gluing of B1 and B2 must be mapped to the product of these elements. That's exactly what you would get from exponent of the integral over B1 glue B2 of the pullback. Well, the integral over the union of two sets is the sum of integrals. And the exponent of the sum is the product of exponents. So altogether, you see precisely the composition of Bordisms is a map to the composition in this category. Where is this category? In this category, in this D for delooping. So here, composition of dimorphisms is just their product in the Lie group. So in U1, this will be a product of complex numbers of absolute value 1. And that's exactly what you want. So again, the integral is pretty much the only such construction with such a property. Okay, more questions?
What about the role of differential cohomology in this setting?
Well, I mean, this Gaussian complex, of course, is also the chain complex that computes a differential cohomology, because differential cohomology is just sheaf cohomology with coefficients in this chain complex. Right? So the differential cohomology is just a sheaf cohomology with coefficients in the Gaussian complex. That's how it's defined. So one interpretation here is that these, let's see, morphisms here, and here, remember, it's important that we work on this d-dimensional site. Morphisms in this to this object will be basically computing differential cohomology. I mean, this is basically the correct, as you can see from this resolution, it is the correct incarnation. I mean, you can rightfully refer to the derived mapping space let's say BDU1. You could call it actually the differential cohomology of S differential cohomology. This is differential cohomology by definition, more or less, yeah.
Okay, thank you.
Okay, more questions? Okay, so this takes care of the first part of the recipe. How to compute V cross D. We have several examples now. I can also mention some other examples. For example, vect. If V is a vect, let's say some vector bundles or fiber-wise vector bundles of some fixed dimension n, for example, or even non-fixed, doesn't matter, then V cross 1 will be again, we'll have two different models. One model will be just, if you want, fiber-wise vector bundles of dimension n, and the other equivalent model will be fiber-wise vector bundles with a fiber-wise connection of the same fixed dimension n, and connection preserving isomorphisms. One moment. Yeah, sorry, fiber-wise vector bundles, fiber-wise trivial. Yeah. Anyway, let me not even mention this model. This is easier to state. Fiber-wise vector bundles with a fiber-wise connection and connection preserving isomorphisms. Well, you may say again, how could this possibly be equivalent to just vector bundles if here I have vector bundles with connection and connection preserving isomorphisms? We know these are not equivalent. So what's going on here? Well, what's going on is that fibers have dimension 1. And a connection on a vector bundle over a one-dimensional manifold, it has a very simple structure. It's precisely a trivialization of this vector bundle. So, I mean, cyclically, this groupoid, because the dimension of the fiber is 1, is equivalent to the groupoid of, I guess you can call it trivial vector bundles, where trivial means not just on objects, but also on morphisms. So it's a groupoid where objects are just a single object, which is a trivial vector bundle, and morphisms will be just linear maps from the fiber to itself, which you extend to a morphism of the trivial vector bundle to itself. So morphisms are just linear maps of some typical fiber. So trivial or trivialized maps. And this example is computed in exactly the same manner as what we have here. The only difference will be in the very final formula. Instead of this expression, you will quite literally take the parallel transport. So you will have the same type of data. You have a vector bundle with a fiber-wise connection omega, a map F from V to U, and the bordism B, and you will send it through the parallel transport along the bordism. See how can I write this down? Parallel transport along the bordism B of what? Of the vector bundle with connection given by the form omega. So this will be a linear map between fibers. That's what your action functional is. So that's there's of course also a similar example for principal G bundles. I mean, it's all the same. Okay, so this takes care of the first part of the recipe, and I guess now we have a question, which is, do we want to continue today? Because there's probably almost certainly will be no lecture. I will know for sure on Tuesday, I guess, but almost certainly there will be no lecture on Sunday, May 12th, and possibly no lecture on, but I'm not totally sure yet what, on Sunday, May 17th. And that would mean we have a break of 3 weeks at least. Or maybe another option is I can try to finish part 2 of the recipe today. Part 2 of the recipe, just this is will be part 2b here, which we will make an explicit computation for 2-dimensional or d-dimensional functorial field series. And that would be another option, but it's up to you guys what you want.
I would like to continue.
In right now, you mean continue right now?
Yes, right.
Okay. Any other options? Any other opinions? Like,
So I have to leave soon, but for me it's fine if I just look at the recording afterwards, because it will be posted anyway. So
all right. Any other opinions? Okay, yeah, we can. Let's continue, and let me do part 2B of the recipe. So let me pick some interesting geometric structure. Let's say S will be a geometric structure that sends T over U to the set of fiberwise, let's say flat Riemannian matrix. Flat means vanishing curvature. On T over U. And even dimension 2 example is already interesting. This will be a flat matrix on surfaces. So that's already interesting. So this is an example of an unenriched structure. And this is a sort of connects to the question by Alex an hour earlier. And let's say we want to do some computations, and ultimately we want to compute this mapping space for some target V, doesn't matter which one. And what we are going to do is, let me maybe phrase it this way. So what we are interested in here, we have sheaves on the unenriched side, the adjunction I previously mentioned, to sheaves on the enriched sheaves on the enriched side, and one more adjunction to, or Quillen equivalence, in fact, to sheaves on the Cartesian side with volleys in simplicial sec with the action of OD. Okay. So how do we compute with something like this diagram? So the way this is going to work, I'm going to so S, our choice of S is an object here. And we are interested in moving here along this, so this Quillen adjunction, this Quillen equivalence. So let me first notice, let me call this, I don't know, R. I guess I can call this R star, R for restriction. Let me first notice that the composition of R star, which is a Quillen equivalence, and iota shriek, this is a homotopy co-continuous functor. And because this property that will allow me to compute the image of S in this category here. And the very first step in the construction will be the Koyonega lemma. So step 1. So we are computing. So we are computing our scar of iota shriek, which I guess I can call maybe some easier to write notation, maybe a curly C, apply to S. So why do we want to compute this? Well, when we finish the computation, you will see the answer here will be something very simple and easy to interpret. In fact, I can tell you it will be a second Lie group. And we will interpret this when we get to it. So the answer here is going to be much easier than the this S here, which may not be entirely obvious how to work with. So step 1 in the computation is the Koyonega lemma. It tells you that every pre-sheaf, like S, is a homotopy colimit over representables T over U, mapping into your pre-sheaf. And here you have the Yonega embedding. So that's completely abstract Koyonega lemma. Next, I'm going to restrict to a smaller subcategory. So first of all, let me point out that we can harmlessly restrict to projections or the form RD times U over U. So why can we restrict to such objects? Well, it's the usual argument with good open covers. So every open cover can be refined by a good open cover. So Cartesian spaces are sufficient. Or maybe a bit more fancy, you could say I can restrict to sheaves on the Cartesian side here. And this restriction map is a Quilling equivalence. So I can compute here instead of here. And of course, there's an analogous enriched version. And an analogous injunction here. Well, everything is completely analogous, so I might as well move here and work with this site where objects have this form. And what's more, I can do even better. I can identify this, so RD with a flag metric. If you think about how flag metrics work, every Riemannian manifold with a vanishing curvature, vanishing, I guess you can call it sectional curvature. Well, that's just locally looks like RD with a standard metric. Locally looks like RD with a standard metric. So in addition to requiring that you have RD here, I can also require that given that the metric on RD at least locally looks like a standard metric, I can require that this metric here, let's call this so this map to S, remember, is a sheaf of fiber-wise Riemannian metrics, and any such Riemannian metric locally looks like an open ball in RD of some positive radius. So we can require this metric can require the metric to be isomorphic to a metric on open balls in RD with a standard metric, and the radius will be controlled, or the radius will be some maybe real number, yeah, of radius R. Because every manifold with a flat Riemannian metric with vanishing curvature can be covered by such open balls with a standard metric. So here I should say with standard metric. Right? So that's the other considerable simplification. So this type of argument is once again a good open cover argument. Now, this category here I mean, it has an explicit description, right? So the indexing category, let me move on to this page. If you stare at this for a while, you will see that the only objects we have are open balls, or more precisely, families of open balls of some fixed radius r greater than 0. And I guess in principle I should have said maybe the radius is a smooth map from U to R greater than 0. Although I'm not totally sure if that's necessary, but let me stick to what I know. And morphisms, well, morphisms a priori are, so what are the morphisms in this category of elements, or if we prefer the comma category? Well, a priori morphisms, let me do a little side here. A priori, they should be just inclusions or fiber-wise open embeddings that commute with a map to S. So in other words, this map is a metric preserving. Or an isometry, I guess I should say, more conventional terminology, isometry. So morphisms will be embeddings, isometries, or I guess metric preserving embeddings of open balls into other open balls. And how many such embeddings do we have? Well, it is possible to give a complete description, right, of such such embeddings, such an embedding, the morphisms from R1 to R2, the two families of radii, these will be given by, well, embeddings. So let's say R1 is a function from U to 0 infinity, and R2 is a function from V to 0 infinity. Well, these so morphisms will be given first of all by a function f from U to V. And then I will also need G. G will be a smooth map from U to the Euclidean group of dimension D. So let's recall this is just automorphisms of RD with a standard metric. So you have translations plus rotations, basically. And reflections, I guess. The Euclidean group, yeah. So the interpretation here is really simple. Let's ignore U and V. These are just control families. So G, an element in the Euclidean group, tells you how a ball of radius R1 embeds into a ball of radius R2. What you do is you look at the ball of radius R2, which is here the coordinate system maybe, and to embed a ball of radius R1 into it, first you have to tell me where the origin goes. That's the translation part. And you also have to tell me how you rotate the ball. So that's an element of the orthogonal group. So by the way, this is the semi-direct product. I guess you can say RD semi-direct product OD. You also have to specify an element of the orthogonal group that tells you how the ball rotates, like this maybe. So that's what the element of the Euclidean group does for you. And there is a restriction. Let me write it in words. The image of B of radius R1 under G is inside B of R2. You do have to specify an embedding, so you must be within your codomain. And this completes the description of the category equivalent to this category here. So just to reiterate, objects will be smooth families of open disks of some radius R, or family of radii. And morphisms will be smooth families of embeddings of one disk into another. And this category will be equivalent to this comma category here. And we take the same omega of RD times U over U here. Let me ask if there are any questions so far in this complication. Everybody happy? Or everybody lost? Or everybody tired, maybe? I don't know.
A bit lost, maybe.
Okay, at which part we should restart?
I think the last equality. So
This one?
yes, yes.
So the only thing that happened is we took this indexing category and provided an equivalent category to it. More specifically, the first observation was that once we restrict to, so here, objects are morphisms from a representable pre-sheaf of Rd times U over U to S. So in other words, objects are such objects in the cyclem D together with a fiberwise Riemannian metric on Rd. And without loss of generality, we can require this metric to specify an open ball. So maybe Rd is no longer the best notation because really we just want an open ball with some fixed radius. And the only observation we can make here is that isomorphism classes of such open balls, they are uniquely specified by the radius. So this description here completely describes all possible objects in this category. There are no other objects once we restrict to metrics that describe open balls. So every smooth family of open balls is uniquely determined by its radius, or family of radii. That's where this thing comes from.
Okay, I think I get the rest of the idea now. Thanks.
Mm-hmm. Yeah, and for morphisms, it's also exactly the same reasoning. Morphisms are embeddings preserving metrics, and there are very few such maps in this category here. And they can be explicitly described as just you rotate the ball and translate it. So that's an element of your Euclidean group. Okay, so let's move on. I guess let me continue with this homotopic limit here. So it's a homotopic limit over this category that we just described. So objects are R and morphisms are F, G. So let me write it in fact in this way. R and morphisms are pairs F, G of omega Rd times U over U. Okay, so this, just to remind you, is weakly equivalent to S. Now, our goal was to compute this functor, C applied to S. C is this homotopy co-continuous functor that sends a representable pre-sheaf here to the corresponding representable pre-sheaf here, and then here it will become, well, let me just show to you what it will become. So C of S is C of this homotopy co-limit, and C is a homotopy co-continuous functor. So we can move C inside of the homotopy co-limit. So it's the same indexing category. And what is C of such a representable? Well, C is, just to remind you, R star of iota shriek. Iota shriek of a representable will simply produce the same representable but in the enriched sense. And then R star, just to remind you, R star restricts to the another subcategory, which is its only object is this object, and morphisms will be just rotations of Rd. So altogether, we see that we get this group OD times the representable presheaf of the Cartesian space U, because that's what R star of this representable is, right? So the R star lands in this category, and its value in some Cartesian space will be precisely the simplicial set with an action of OD, where the simplicial set itself is the value of this representable on the corresponding object. Well, maybe I should just quickly write it down for you. So R star of this will be a presheaf that by definition is given by restriction. So it says a Cartesian space V true enriched set of morphisms or smooth set of morphisms from RD times V to RD times U. That's how representable presheaves work. And by the Kister-Mazur theorem, like I think I mentioned before, this smooth set is weakly equivalent to just, well, let me say maybe smooth maps from V to U times the monoid, enriched monoid of embeddings of RD into RD. And finally, so now Kister-Mazur tells you that this is the same as OD. And that's how OD showed up here. And this term is, of course, precisely the representable presheaf of U, right? So V is arbitrary. So maps from an arbitrary Cartesian space to U, well, that's the representable presheaf of U. Okay, any questions so far? Oops. So let me now compute further. So this is a product with a fixed simplicial set. And such an operation is a homotopy co-continuous operation. So I can say this is OD times the homotopy co-limit of this. Okay. So how can we compute the homotopy co-limit of a diagram? This is just an ordinary category, by the way. A diagram of sets, or in our case, presheaves of sets. Well, the homotopy co-limits of presheaves are computed object-wise. So really, we have to compute a homotopy co-limit indexed by some ordinary category of a diagram of sets. We know how to compute this type of homotopy co-limit because this is by Thomason's Thomason's construction or Thomason's theorem can be computed as a Grothendieck construction. Of this diagram. So let me keep carrying this OD around, but now the pre-sheaf will send, and I guess at this point I started using W in my notation. So it's a pre-sheaf that sends W to the nerve of the following category, namely, its objects will be radius R, a map from U to 0 infinity, and F, a map from W to U. So where did F come from? F came from the representable pre-sheaf here. So remember, here we are evaluating on W. The value of this pre-sheaf on W is just smooth maps from W to U, and that's how this map gets incorporated into Grothendieck construction. And morphisms between two such objects, so RF to R1F1 to R2F2, will be precisely pairs, I guess. First of all, you will so R1 will be a map from U1 to 0 infinity. R2 will be a map from U2 to 0 infinity. And F1 will be a map from W to U1. And F2 will be a map from W to U2. So the gate of such a morphism will be a pair. H will be a map from U1 to U2. A smooth map. That's also induced by the Grothendieck construction. And there will also be G. G is the same G as, of course, we had already here. That's what morphisms in the Grothendieck construction are. I guess, sorry, I should have called it F probably. Yeah. Yeah, I'm really sorry, but this should be probably called F. Could be, okay, this is really bad. Well, yeah, sorry, this H here corresponds to what I previously used to call F. All the way up here, F was a map between indexing families of two radiuses, radii. So unfortunately now I screwed up the notation, and maybe it's not too late to fix it. Let's see, is it too late to fix it? F, maybe I should not call it F, but F is taking, G is taking, H is, maybe that's what I should call H. Yeah, very sorry, let me fix it. And now this is rightfully can be called F. Much better. And G will be a map from U1 to the Euclidean group. So that's what a morphism is. That's a gate of a morphism, and the conditions that have to be satisfied are: one is a stupid condition induced from the Grothendieck construction, is that the diagram consisting of W, U1, U2, H1, H2, F, this diagram must commute. And the other condition is that yeah, maybe I can write it inverts the image of an open ball of radius r. Indexed by the radius, I guess, r1. Under the map G. And notice R1 and G both have the same indexing parameter space, U1, so that's perfectly legitimate, is inside the open ball of radius R2. So this condition simply migrated here from the original description right here. It just migrated using the via the Grothendieck construction. And this condition was simply supplied by the Grothendieck construction. That's how you construct the Grothendieck. That's what the Grothendieck construction is, really. Okay, so this notice what happened here is we lost the homotopical limit. The homotopical limit disappeared. We computed, in a sense, the homotopical limit as this formula. So what I wrote so far is just follows out directly from the Grothendieck construction. But of course, it is possible to simplify it further. So maybe let me observe the obvious simplification here. So simplify. If you look at the data, what falls out from the Grothendieck construction, you will see that there's extra parameter space U, but it does seem like somehow you can compose H and R to get this single map from W to directly to zero infinity, and that's exactly what you can do. So what you can do is you map an object RH to just composition R composed with H. This will be a map from W to 0, 1, 0 infinity, sorry. And likewise, a morphism FG from R1 H1 to R2 H2. You can map it to yeah, you can map it precisely to G precomposed with H1. And this will be a map from W to the Euclidean group. So the whole category constructed, maybe I should have said this is at least homotopy equivalent to. This whole category was simplified to a much easier category, namely W now gets sent to the nerve of the category with a much easier description. Objects will now be, let's say, smooth map capital R from W to 0 infinity. And morphisms now will be smooth maps, let's call them G, capital G, from W to the Euclidean group. And yeah, so this functor implements an equivalence of the category on the previous page, written down using the Grothendieck construction, and this much easier category. And of course, don't forget about restrictions on morphism. So G is a morphism from R1 to R2. And you require that the image, the usual image condition, the image of the ball of radius R1 under G is contained in the ball of radius R2. Okay, so this takes care of the second stage of the computation, and now we are really close to the final answer. Let me now ask if there are any questions about this stage. Is contained in. Any questions about what we did so far? Is everybody comfortable with stuff like Grothendieck construction, Thomason's theorem? Well, Thomason's theorem simply shows that the homotopical limit of a diagram of sets or categories can be computed as its Grothendieck construction. How is everybody? Is everybody lost by now, or totally confused? Not totally confused?
If it is possible, we can maybe review Grothendieck construction. Although
yeah, no, it's really easy. So let me review it in green. You have a functor f from some indexing category I to the category of categories. Well, I guess here it's really just a pre-sheaf of sets. So the Grothendieck construction for such simple functors is just the category of elements, which is another name for the comma category. So the Grothendieck construction in this case degenerates into the category of elements, so objects will be pairs consisting of an object I in capital I and an element X in f of I. And morphisms will be so from Ix to I prime X prime will be by definition morphisms I from I to I prime F with a condition that capital F of F applied to the element X equals X prime. So that's what the Grothendieck construction amounts to. It's literally another name for the category of elements, or in this case, co-pre-sheaf, right? So of course I could have taken the opposite category. Well, in fact, it's not, yeah, sorry, it's really the category of elements of a pre-sheaf. Yeah, category of elements of a pre-sheaf, yeah. Well, the traditional Gherkin construction would have, instead of sets, would have categories here, and it would be a very similar description. X would be an object in this category. And then instead of an equality here, you would have an morphism here. That's the only difference.
And could you recall the Thomason theorem?
Oh, the Thomason theorem quite literally says, Thomason theorem says, if I have F, a diagram of categories, where categories are equipped with a Thomason model structure, meaning weak equivalence is a functor whose nerve is a weak equivalence of simplicial sets. Or if you prefer, you can actually compose it with a nerve functor and Lang and simplicial sets directly. Then the homotopic limit of this composition, so nerve composed with F, is weakly equivalent to the nerve of the category given by the Gherkin construction of F. So to compute the homotopic limit of a diagram whose a diagram of simplicial sets whose objects are nerves of some categories. And the diagram itself is induced by a diagram inside a category of small categories. You can compute it very easily by taking the Gherkin construction of this functor and check its nerve.
Thank you.
Right? Any more questions? Okay, now we are ready for the final step in the proof. I'm going to write down a map to a much easier category. Well, not much easier now, I guess, but still easier. And I'm going to show it's a weak equivalence. So the map will go to a pre-sheaf. Now it will be really stupid. Instead of the nerve of a category, I will have a de-looping of a group. Which group is it going to be? It's going to be the group of smooth maps from W to the Euclidean group. Okay, 1, 2, 3, 4, yeah. And what is this map? It sends an object R to the only object in the loop in the what is usually denoted by a star. And it sends a morphism G from R1 to R2 to, well, G itself, again, because G is a smooth map from W to the Euclidean group here. I mean, this is precisely a morphism here. So you send it to G itself, and you simply forget the condition that the image of one ball is contained in the other ball. And the claim here is that this functor, let's call it, I don't know, pi for projection. Pi is a final functor and hence induces an equivalence on nerves. The nerve of pi I guess here, well, anyway, doesn't matter, is a weak equivalence. So this map is a weak equivalence here. Well, how can we see that pi is a final functor? That's what is called equivalence theorem A. It's a criterion for final functors. Let me state it in general first. You have a functor f between two categories is a final functor. So final means colimits along D can be computed as colimits of the so if you have a D index diagram, colimits of this diagram can be computed by restricting along F and computing the colimit of the C index diagram. Is final if and only if for every object in D, the comma category D over F has connected. Well, I guess here I really need infinity final. So I should say has weakly contractible nerve. Weakly contractible means the nerve is weakly equivalent to a point. Well, and what is the comma category? Again, D over F. D over F, it has objects, pairs C, comma X, where C is an object in capital C, and X is a morphism from D to F of C. And morphisms from C1x1 to C2x2 are precisely F, a morphism from C1 to C2, such that the diagram with x1, f of C1, x2, f of C2, and f of F commutes. That's what a comma category is. What is the big name? Okay. So let's keep this criterion for finality here, and let's compute the comma category of this functor. Now let me concentrate on the part that matters, which is this part and this part. So I have a functor that sends R to the only object here. And it sends G, a morphism from R1 to R2, to itself. And we are computing the comma category according to this recipe. The only object in the target category is a star. And I want to compute its comma category over this projection pi. Well, it has objects by definition R and R. An object in the source category is R. And you also have X, a morphism in the target category. Which will be a morphism from star to a star. I mean, it's really just an element of G, right? So a smooth map from W to the Euclidean group in our case. And R, by the way, I should say maybe R is a morphism from W to 0 infinity. And morphisms from R1x1 to R2x2 will be they will be this morphisms G. It will be this morphism G from R1 to R2. And the triangle must commute. So a triangle here, well, it's all objects will be scars. So it's kind of a typical triangle. And here I'm going to have x1, x2. Here I'm going to have pi of G. So in a more conventional notation, what we are simply saying is that G composed with x1 equals x2, where composition is the pointwise composition in Euclidean group. Okay. Okay, so what is the geometric interpretation of the comma category? How can we see it more concretely? Well, the way I prefer to think about this is that an object r comma x, well, r is some radius which specifies an open ball, and x is an element of the Euclidean group, unrestricted. So x is not restricted like G. So I think of this as an open ball. So Rx, R comma x, is an open ball of radius r in position or placed in position x. So x is an element of the Euclidean group. You can act by this element on the open ball, and it will move it to some position inside Rd. Inside Rd. And then a morphism. Notice, because of this condition here, this implies G equals x2, x1 inverse. A morphism, if it exists, is uniquely determined by its source and target. And the geometric interpretation is really simple. Morphisms are inclusions. Either one ball is a subset of the other, in which case a morphism exists, or it doesn't, and then a morphism does not exist. So this G is uniquely determined by its source and target. Okay, so the geometric interpretation of the comma category is precisely the category, or more precisely, in our case, it's even a Poe set. This is really a Poe set, whose elements are open balls of some fixed radius placed inside some position in Rd, and morphisms are inclusions.
So why do we have an inverse map?
Inverse map is the inverse in this group. This is a group which has an inverse.
Okay.
It's a pointwise inverse, so for every point in W, you take the inverse. Well, the remaining claim is that this comma category is filtered. And the nice thing about filtered categories is that they have contractible nerves. The nerve is weakly contractible. So why is it filtered? What does it mean to be filtered? Being filtered, well, for a POSEC, it means you pick two elements. So a POSEC P is filtered if for any true elements there is a third element such like x is equal z and y is equal z. For any true elements, you have an upper bound. In our case, elements are open balls inside RD, and for any true open balls inside RD, no matter what position, you can pick a bigger open ball that contains them both. So indeed, this POSEC is filtered. Therefore, the comma category has a weakly contractible nerve. So in our case, any true open balls in RD are contained in a bigger open ball. Therefore, the comma category is filtered. Therefore, it has a weakly contractible nerve. Therefore, the functor pi is a final functor, or infinity final functor, actually. Therefore, its nerve is a weak equivalence. And therefore, this map here, which we also call pi, this map is also a weak equivalence. So we computed the homotopy colimic as OD times this presheaf. But this presheaf is just a representable presheaf of a Lie group. So I can rewrite the answer, this answer here, as can be rewritten as OD times the de-looping as a Lie group. So this is a de-looping as a Lie group of the Euclidean group. Okay, this completes the computation. So just to remind you, what we computed here is C of the flat Riemannian matrix. So that's another name for R star iota shriek S. What's the point of this computation? Well, the point of this computation is the following consequence, which I'm going to write on this page. Functorial field series of dimension D with geometric structure S and the values in some infinity D, smooth symmetric monodic infinity D category V can be computed as, so by definition, are maps from the Bordism category to V. Then by adjunction, it will be maps from S to V cross D. And then by equivalence, and maybe I should have said this is the same as R map. So we are now switching to a third category, which is sheaves on Cartesian spaces. So let me write down the category in which this happens. So this one is smooth Yeah, we are losing participants fast, so let me finish very quickly. There's 1 minute left, maybe. Smooth symmetric monoidal infinity D categories. This is sheaves on FEMD, unenriched. Now, according to this complication, I can write down R star iota shriek S, R star iota shriek V cross D. And this will be sheaves on Cartesian spaces with values in simplicial sets with the action of OD. Now, using this complication we just did, here, I can compute this as R map from OD times a B Euclidean group. And we already know, so we are in the same category as here. And notice we have OD equivariant maps out of an object that has a free action of OD. So this is going to be the same as R map from just B of Euclidean group with values in this. And this we already know how to compute. We did some complications of V cross D before. And this is just a restriction functor. In fact, sorry, I should have not, I may have been a bit careless because, of course, the way we compute V cross D is already defined on the enriched side. So I should not confuse you with unnecessary functors. So it's just restriction. This is just a restriction functor. So this is very computable. And so what is this R map in more simpler terms? This is quite literally homotopy coherent representations of the Euclidean group with values in the automorphism Lie infinity group of some object X, where X is an object. X is an object of V. More precisely, in our case, it will be a fully generalizable object. Yep, and I guess that's a perfectly good point to stop. Oh, yeah, we really went over time today, sorry. I guess I didn't realize just how much time this argument would take. Okay, any questions?
Why can we remove the term O of D?
Yeah, because the action of OD on such a product is a free action. This is literally a free OD action on this object. Therefore, so here, we moved, yeah, I'm really sorry. We moved to sheaves on Cartesian spaces. No longer with values in simplicial sets with an action of OD, but just simplicial sets. No action anymore, just the action went away. When we, I really should write this here. So this, at this point, we move to simply sheaves on Cartesian side. So here, the action went away. Maybe I should just move it here. So we are working with sheaves of simplicial sets on the Cartesian side, and the action went away because it's a free action. So OD equivariant maps out of this are the same as ordinary maps from this object alone.
Okay, and the equivalence above from R star iota shriek S.
That was computed here, right? So R star iota shriek S.
Yes, but we have equivalence with the derived map between S and V D.
Yeah, so this term is equivalent to this term, right?
I mean the equivalence above. Just yeah.
Oh, I see. Well, here, yeah, I should have been a bit more careful here, but the point is that I could have written it, I guess, this way. I should have maybe inserted an additional intermediate step. So here I can harmlessly insert iota shriek. So R star is a quilling equivalence. So it's harmless to insert this quilling equivalence in front of both arguments. And that's what happened in this step here. Iota shriek S mapping to V cross D is the same as put R star in front of both. Since R star is a quilling equivalence, that's a harmless thing to do. It will not change the answer.
Yeah, okay.
And the way I shriek got in front of, this is just maybe a tautology, but as maybe another step. I mean, you can pick either formulation as your favorite, but you can also put like I upper star V cross D. This is just how to formulate the GCH, geometric cobordism hypothesis for unenriched geometric structures. You can formulate in two equivalent ways. You can either say promote it to an enriched structure using iota shriek, and then apply the GCH in its formulation for enriched structures. Or alternatively, you can say just restrict V cross D to an unenriched pre-sheaf using iota upper star, and then compute morphisms of unenriched pre-sheaves. And because of the adjunction between iota shriek and iota upper star, it's the same. So pick your favorite formulation, but either one of these will qualify as GCH for unenriched structures.
Okay.
Yeah. In fact, I think the way we mentioned this, we said we promote it to an enriched structure, so that's exactly the correct thing to do here. Yeah.
Another question. I forgot what do you mean by B of C infinity something?
B of C infinity. Let's see, where is B of C
Above?
infinity? What was the last C infinity? 1 moment. Oh, you mean here?
Yeah.
This is just a D looping. So B in general, guess, let me maybe formulate this. There's a equivalence between pointed simplicial sets and simplicial groups, for example. The right adjoint functor is a well-known functor called loops omega. This is loops loop group, maybe, if you want. This is just our map.
I see. We use the fact that C infinity or something. It is a simplicial group, and
Yeah.
we apply D and gets a simplicial set. Okay. Okay.
Yeah, so the left adjoint is called B.
And the last question?
Yeah, so,
About the term below at the end of these notes.
okay, let's see.
Yeah.
Here?
At the end.
Yeah.
We have a map weak equivalence with maps from
Yeah. And what's the question?
I have a question about this equivalence, the last equivalence.
Yeah, so what is a morphism? Yeah, this is literally, well, there's a missing step, of course. B is a left adjoint to what? To omega, if you want. Well, I mean, okay, so strictly speaking, this is not quite right, but here we work with sheaves, if you want, sheaves of simplicial groups on card. Why is it not quite right? Because first, the base point, so this simplicial object has a unique base point, and this base point is mapped to some point here, which will pick an object X for you, which will be a fully generalizable object in X, in V, sorry. And so what I really should say is loops based at X here. And then you move B to the right, it becomes the loop group functor. The loop group functor is just another way to loops of X is literally just extracts the group of automorphisms of X in the infinity sense. And B being right adjoint to loop, well, that gives you precisely homomorphisms. So this is a homomorphism of sheaves on Cartesian spaces, valued in simplicial groups from the Euclidean group to the group of automorphisms of some fully generalizable object X. So it's precisely a homotopy coherent representation of the Euclidean group on X.
So this out of X is by definition this omega X of this stuff.
Yeah, I mean, that's another name for, I mean, loops in an infinity group like, well, that's just another name for automorphisms of an object. Because what is an automorphism of X? It's a morphism from X to X, right? And what is a morphism from X to X? Well, in the nerve, it will be a one simplex whose endpoints are both the vertex X. And this one simplex is another name for a loop, right? That we wrote down somewhere. I forget where. Here, yeah. Yeah, so loops in the nerve of an infinity groupoid based at some point corresponding to an object X. Well, that precisely computes the infinity group of automorphisms of X.
And it is true for any R star VD cross, or
Yeah. This is a statement for a completely general target.
so we can replace this R star VD cross by what?
Well, it depends. It
The
depends on
general
your
state.
choice it depends on your choice of V, right? So, for example, if V is vector spaces, then you would literally get a representation in the usual sense.
Okay.
So if V is vector spaces, you see just a vector space, finite dimensional even, and you have a representation of your Euclidean group.
Okay, thank you. So thus we prove that. Could you recap briefly?
So the point is a functorial field series of this type with this geometric structure S being given by flag Riemannian metrics are equivalently homotopy coherent representations of the Euclidean d-dimensional group on some object X and some fully realizable object X.
Okay.
So now this reduces the problem. I mean, of course, imagine, I don't know, substituting, I don't know, the flag Lorentzian matrix, right? So so you can do exactly the same computation if you take instead of Riemannian, you can take Lorentzian, and then you get what is, so the Euclidean group replaces by what is called the Poincaré group of dimension D. That's the group of automorphism of the Minkowski space time. Then you will have its representation on automorphisms X. That's basically what an elementary particle is, more or less. Kinda, yeah. Well, at least if it is irreducible.
Also, I want to ask you about sending links for downloading the last two lectures and counting this lecture, since I have a problem with a recorder on current lecture and in the last lecture.
Yeah, I can send you links. Just send me an email.
Possibly or in Discord or in email for downloading.
Yeah. Okay, more questions? Okay, let me stop the recording now.